Today we'll be discussing the moist equation of state. In a previous video, we discussed the equation of state, which is defined as pressure is equal to density times the dry air gas constant times temperature. However, in reality, air is not just dry air all of the time. Sometimes it can have water vapor, which is the gas form of water, in the gas as well. So we can imagine a situation where we have a block of air where one half is comprised of only dry air and the other half is comprised of water vapor. And for the right side, 100% is water vapor, 0% is dry air. Well, it's the opposite on the left side. 100% is dry air and 0% is water vapor. However, for the entire block, it's 50-50. 50% water vapor, 50% dry air. So to define this situation, we can first define a few variables. We have md, the mass of dry air, mv, the mass of water vapor, and m, the total mass. We have the dry gas constant from previously, but now we're going to include the water vapor gas constant. And we're going to derive the moist air gas constant, which we can then use in our equation P is equal to rho Rm T. So we can define Rm as a linear combination of dry air mass, dry air gas constant, water vapor mass, and water vapor gas constant divided by the total mass. And splitting up the terms by dividing out m for both addition terms, we come up with md over m rd plus mv over m rv. And we can define mv over m, the water vapor mixing ratio, as Q. And we can also show that the dry air mixing ratio, md over m, is equal to 1 minus Q, or 1 minus mv over m. So to get this, we use a little trick. We know that m is equal to md plus mv. So we take m over m, which is of course equal to 1, and we make the top, we apply m is equal to md plus mv to the numerator, then divide out the terms, we'll get md over m plus mv over m, which is just equal to q, is equal to 1. And now we can subtract q on both sides, and we're left with the dry air mixing ratio md over m is equal to 1 over q. And that's just in a situation where we only consider dry air and water vapor. Now this might change if we have liquid water, like a raindrop, inside of air. That's going to change this equation again. But for now, we're just considering the gas. Liquid, of course, is not a gas, so it's a more simple situation in this case, but definitely more complicated than the equation of state we learned previously. So now, using the fact that md over m is equal to 1 minus q, we can plug that into this term, giving us this equation. And then we know by laboratory experiment that the water vapor gas constant is equal to the dry air gas constant divided by 0.622. And of course, there's many more decimals to this, but there's 3 decimal places is a pretty good approximation. And this, of course, is another approximation. We could maybe figure out an equation for RV itself, but I think at this point there is not an easy way to figure that out. So laboratory experiment is probably the best way. And I'm assuming that this was derived by using some sort of linear regression. So they have a bunch of, they calculate RV and they calculate RD, and they get a bunch of different points, and they make an approximation of the mean of those points. Of course, there's going to be some variability, but this does work as a good approximation for most of the time. So now plugging in that for RV, we're left with an equation with only RD in it. Now we can distribute. We can take the 1 over 0.622 RD Q minus QRD, write that in the better order, 0.622 QRD minus QRD. So that gives us this 1 over 0.622 minus 1 term times Q. And then we're also left with the 1 times RD. 1 times RD. So that's where the 1 comes out. And we've also taken the RD out already. So instead of QRD, we put it out here. Instead of RD, we put it out here. And this term, by simple calculation, is 0.608. And now we have that the moist gas constant is equal to 1 plus 0.608 times the water vapor mixing ratio as a constant applied to the dry air gas constant term. So now we can write P is equal to rho times RMT, which expanding is rho times 1 plus 0.608 times the water vapor mixing ratio times temperature times the dry air gas constant. And we can call this term here the virtual temperature, which in other words is the temperature dry air would have to have the same density of moist air at a given pressure. So you keep the pressure the same. You want to know how much temperature dry air would have if it had the same density of moist air being there. So you can see from this definition that this equation is an approximation. Since it's difficult to calculate the water vapor, we instead use this idea of what temperature would it have if it had the same density, and that's why we see here only the dry air gas constant with some other term here that is different than, we could have stopped the equation here, but some of these terms might not be very easy to calculate, and so we can use this form. Okay, in the next video, we will be discussing the moisture continuity, which is similar to an equation called the mass continuity, which we will also discuss a little bit, but also at another time. Thank you, and stay tuned.